Hey, IB students. We are beginning our study of trigonometry and geometry, which is topic 3 in our IB syllabus. So we're going to take some examples of trigonometry problems and use those to kind of reinforce some of the lessons that we learned back in pre-calculus. What you want to have handy is our formula packet, and we are in section 3. And then you also would like to have handy the reference sheet that I created for you, which is probably in yellow. And so let me go over quickly what I put on the reference sheet. Remember, you won't have this available to you when you take your exam, but up at the top are our 3 parent functions you need to be aware of: sine, cosine, and tangent. Underneath that, an example of a transformed function, including definitions of midline, amplitude, and period length. There is a miniature version of our unit circle. If you flip that over, when you solve law of sines and law of cosines problems, students tend to have trouble with the ambiguous case, so I included some notes in here on how to handle the ambiguous case. Underneath that, a little refresher just in case you forgot on what SOH CAH TOA is. So your ratios for sine, cosine, and tangent, and then also your ratios for special right triangles. And then lastly, underneath that, some tips for solving trig equations if you're having any trouble. Okay, so let's take a look at the formula packet. So in our formula packet, the very first topic, 3.1, is actually geometry. That's going to be a separate video. So what you're going to be seeing in the trigonometry unit are things like sine rule is what they're calling law of sines, the cosine rule, which is law of cosines, area of a triangle, length of an arc, area of a sector. On the next page, you've got some identities. So you have your tangent identity, your Pythagorean identity, and then your double angle identities. And then everything after that is HL only. So those are the only things that you are responsible for. So let's take a look. I'm going to split this up into multiple videos, by the way. So this is video number 1. So the first thing we're going to look at is an example of arc length and area of a sector. So the following diagram shows a circle of center O and radius 15 as labeled on the picture. The arc ACB subtends an angle of 2 radians at the center O. That word subtends means that this arc length corresponds to this central angle here. And so the length of the arc ACB is what we are trying to find. So if you take a look at your formula packet, your formula for length of an arc is L equals R times theta. And it's very important that you note that the radius is R and theta has to be in radians. So I'm going to start by writing my formula L equals R theta. And on this particular problem, you are told your radius is 15, and you are told that your theta value is 2. So L is equal to 30. And let's get some units on here. So that is physically the length of the arc length. And so if the radius is in centimeters, then the arc length is in centimeters. So our solution, arc length, is 30 centimeters. Part B, the area of the shaded region. So our shaded region, this is an area of a sector. Most students think of this little guy as the area of a sector, but technically they both are sectors. So you can actually work this one of 2 ways. You can find this a little pi piece first and subtract it away from the area of the entire circle, or you can find what this angle is in here and then use that with my area of my sector. So that's what I'm going to do. So I know that I'm going to start with my area of a sector formula, which is, and this is from your formula sheet, 1/2 theta r squared. And I need to know theta and I need to know r. We already know r because we know our radius is 15 centimeters. Theta comes from finding what this angle measurement is. And so in order to find theta, I know this piece is 2 radians. Well, all the way around in a circle is 2 pi. So theta would be 2 pi minus 2 radians. So you can approximate that if you like, or you can leave that in as an exact number. That's up to you. So for my area, I'm going to have 1/2 times theta, which is 2 pi minus 2, times my radius of 15. squared. And so we're going to clean this up a little bit. So if you want, you can multiply 1/2 into this little expression if you're trying to keep an exact answer. So 1/2 times 2 pi would be pi. 1/2 times -2 would be -1. And then 15 squared would be 225. And then you can distribute from here. So you would have 225 pi minus 225. And of course, you know, I know you guys, you always want to approximate this if you can. So we're going to grab our calculator and we are going to approximate what this number is. Of course, if they were asking you this question on a non-calculator problem, you would leave it in this exact format. So 225 pi minus 225, and we get for our final area 482. I'm going to round to 3 significant figures. So 482. Okay, so we are going to leave this video at this point, and I'm just going to make this a video on arc and sector. And actually, we'll do one more. We can fit one more in here. So we've got the following diagram shows a triangle ABC where ACB is 90 degrees. So we've got a right angle right here. And AB is 3, AC is 2 as labeled on the diagram, and angle BAC is what they're calling theta. So the first thing they want us to do is show that the sine of theta is square root of 5 over 3. So we know sine is going to be opposite over hypotenuse. I don't know the opposite, so I'm going to have to use my Pythagorean theorem to find that. So I'm going to use leg squared plus leg squared equals my hypotenuse squared. So 2 squared plus, I'll just call it x squared, equals my hypotenuse squared. So 4 plus x squared equals 9, x squared equals 5, x equals plus or minus square root of 5, but we're just talking about the length of an actual figure, which would only be positive. So we have square root of 5 for this opposite side. Therefore, sine of theta has to be the opposite side, which is square root of 5, and that's over my hypotenuse, which is 3. So in terms of what they're expecting you to show, this is the supporting work that they're expecting you to show. Okay, the next question says, show that the sine of 2 theta is 4 square root of 5 over 9. I know the first instinct sometimes is when people see 2 theta, they want to assume they're just doubling that answer, but that is not the case. We know sine of 30 and sine of 60 do not have that relationship. Sine of 30 is 1/2, sine of 60 is square root of 3 over 2. That is not double 1/2. So we've got special identities that we can use. Those are our double angle identities. So we're going to go back into our formula bracket and we're going to take a peek. So our double angle identity for sine is 2 sine theta cosine theta. So I'm going to rewrite sine 2 theta. Now when they say show that, you want to pretend like you don't know what this answer is. So starting by recognizing I need to identify sine 2 theta, or an expression that represents sine 2 theta, and that is the same as 2 sine theta cosine theta. Now we already know sine theta, we actually found that on the previous problem. And we can also find cosine theta. Remember, cosine is adjacent over hypotenuse. So my adjacent side would be 2. My hypotenuse would be 3. So we're going to clean this up a little bit. So on top, we've got 2 times square root of 5 times 2. So that is 4 square root of 5. On the bottom, 3 over 3, which is 9. So we're left with 4 square root of 5 over 9. So we had just shown that sine of 2 theta is equivalent to 4 square root of 5 over 9. Okay, and part C, find the exact value of cosine of 2 theta. So if we're finding the exact value, that means they do not want you to approximate that. So I am going to grab one of my double angles again. And with the double angle for cosine, you actually have 3 different versions that you can use. It's your choice. We already know what sine and cosine are, so I'm going to go ahead and I'm going to rewrite cosine of 2 theta as cosine squared theta minus sine squared theta. And I'm going to substitute cosine in, so cosine is 2 over 3. Bring down your squared. I'm going to substitute sine in, which is square root of 5 over 3 squared. And that cleans up to 4 over 9 minus 5 over 9. So that would be negative 1 over 9. Okay. All right, so that is the first half of our trigonometry notes unit. We covered arc length, area of a sector, trig ratios, and also some of our double angle identities. Thank you so much for listening. Stay tuned for the next video on trigonometry.